So let me first give you the context and our result. So the main question we're trying to answer here is, in the case of lattice-based signature, at what cost can we actually get rid of the random oracle model? So we have those two constructions based on the random oracle model. The first one is a hash and sign kind of construction, and the second one is based on Fiat-Shamir transform. So for example, this second work is what we presented last year, the Bliss signature scheme, but this is based on the random oracle model, okay? So can we get standard signatures? The first answer was given by Lubachevsky and Micciancio, but it raised the cost, the size of signature by a factor log n. So we have much larger signature, and moreover, this scheme is stateful. We need to keep up a large tree as a state as we sign on signatures. So this is not ideal. Other schemes came. They're not stateful, but here the size of signatures are very large. So this is based on the bonsai tree technique. And also came other technique where the signature is now reasonably small. So we just have one vector for each signatures. It's basically equivalent to the random oracle model ones. But the public keys and the secret key are still kind of large. And this also impacts the computation time. So last year at Eurocrypt was a very interesting work on signatures introduced by Ball et al. It's called the confined guessing strategy. So we still have kind of large signatures, but we have short public keys. But the technique itself is kind of interesting. So this is a case of lattices. Here we have log n size signatures, log n elements. But the fact is, Ball et al. Actually give two kinds of construction. A first construction, which is generic and give short keys, but shortish signatures. By shortish, I mean this log n factor here. Okay? This construction is generic, so they can instantiate it with both with three kind of assumption: RSA, bilinear DDH, and also SIS, so based on lattices. And then they also give a second construction. But this second construction is not generic. It uses aggregation technique, and those aggregation technique we only have them for RSA signatures and bilinear DDH kind of signatures. But this is really this second construction that we want in practice because, well, they might have slightly larger public keys, but the signature is shorter. And as you sign a lot of time and you only have to keep one secret key or public key, really, this is this second construction that you like. So this is what we try to address in this work. There is this like missing piece in this puzzle here, and we're going to try to fill that up. So again, the issue to build it with lattices is that we don't have aggregation technique for lattices. So our solution will be to provide a third kind of construction that achieves the same as this construction B, and instantiate it using SIS, so the short integer solution problem, which is tightly related to lattice problems. All right, so this is how my talk is going to go. I just presented you the context and result. Now I'm going to present you a new generic technique that is based on this confined guessing strategy of Ball et al. Then I will present how to build such a primitive from lattices, and finally I'll conclude with some future work or open problems. All right. So what is exactly confined guessing, and how can we present it at high level? So I'm going to present it by comparing it to typical construction for standard for signatures in the standard model. So to build signatures in standard model, one way to do this is to start from what we call all but one branch trapdoor function, and we can generically transform them into signatures. And I'm going to present the confined guessing strategy as a similar transformation, except that we add this little property to the all but one branch trapdoor function. It's going to be all but one branch, but once. So both those constructions will provide non-adaptive security. So let me remind you what non-adaptive security means. So don't worry about non-adaptive. It can be upgraded to full security in a very efficient and generic manner. So the non-adaptive security game is kind of simple. There's only 4 steps in the interaction. First, the attacker queries the challenger for message to be signed. And then only he gets a public key of the signature scheme, all right? Then the challenger also responds the signature's queries. And finally, the adversary has to provide a forgery, all right? So just want you to remember those 4 steps. 1 query is to publishing, 3 response, and 4 forgery. So this is the typical signature scheme here. This is how we build typically a standard signature scheme, nothing new, from an all but one branch trapdoor function. So what is an ABO-TDF? So it's a set organized as a tree of function that the public key allows you to evaluate, all right? And the secret key allows you to invert all of them. But this is the real-world key generation. To provide the proof, we also have this simulation key generation procedure where it's going to work all the same, except that the secret key will now allow you to decrypt everything except 1 branch of the tree. And this branch is going to be hard. And distinguishing between those 2 cases, either the secret key, knowing only the public key, you cannot really distinguish in which case you are. So to construct a signature from this, well, it's not very hard. To sign a message, you're just going to invert the function subscript to your message. So you're going to choose a function according to your message and invert it. And the security reduction is kind of simple. So you receive a lot of messages, you put them at the bottom of your tree, and you're trying to see which node are used in your tree, all right? And you identified a new subtree. You identify the roots, you put small O's everywhere. Then you choose one of those subtrees that is unused and publish a public key, and you have generated a secret key where this subtree is supposedly hard, all right? But because none of the messages lies in this subtree, you are able to sign all messages. And then when you receive your forgery, you just hope that your forgery will fall in this subtree. And if it is the case, well, the hard problem is solved. So you've proven the security of your scheme. I just want to mention that because the 2 cases in the real world and the simulation world are indistinguishable, you can also predict exactly the probability that this last property will happen. So this is nothing new here. It has been used in plenty of constructions. So let's now move to the confined guessing and our formalization of it. So basically, we start from the same primitive, except that we had this but once property here. What do we mean by this but once property? So we have the same key generation with 1 more property here. When you're in the simulation case, you can also program one of the function to have 1 specific value on 1 specific input. So this is a but once, all right? Basically, it's not that you're going to be able to invert the function, but you can program it once for free, which is kind of inverting it in an adaptive way. And this allows much more efficient proof using the following strategy. So you receive Q queries, and instead of inverting a function that depends on your message, you're going to invert a function that depends on a random tag, all right? So you pick random tags, and you're going to count in your tree at each node how many tags there are under it, all right? So each time there is a value that is greater than a 1, it means that there is a collision, that somehow the trees going to the tags collide at this level. So I'm going to mark them in black, all right? And everything that is blue, there is no collision. And I'm going to choose the first line where there is no collision at all. And from this line, I'm going to choose a subtree at random as this but one subtree, the subtree that is supposedly hard to invert, all right? But I might have 1 guy to invert in this subtree, but that's not a big deal because I can program my function, my trapdoor function, to a specific value exactly for this tag here. And then I can sign all other messages because all other tags are not in the subtree that is supposed to be hard. And finally, what do? I just hope that the forgery given my attacker will fall in this red subtree. And again, because of the indistinguishability property, I can exactly know the probability for which it will happen. So before I move to the lattice construction, let me explain why this construction is going to be more efficient. So when we look at the ABO construction, this construction can be done efficiently, or the security proof can be efficient only if the tree is binary. And as we need exponentially many messages, that force the depth of our tree to be linear, all right? In this second construction, I don't need that property. I can have trees that have a very large fan-out, and this is how we're going to get more efficiency, because the depth of the tree that we're constructing can be, for example, just logarithmic. And because the efficiency of those ABO or ABOBO construction depends on the depth of the tree, I'm going to get more efficient construction. So before I move to the construction from lattices, let me recall you the two ingredients that we need to add to an ABO to get this scheme with short signatures and shortish public keys. So we need to add this but once property to a typical ABO. That's not very the hard point. Actually, extending the construction to support flat tree is the challenge in the lattice case. So let's go on building those from lattices. All right, so I'm not going to remind you what a lattice is. The only important thing here is that we're working with the short integer solution problem, which is tightly related to lattices. OK, now how do we build trapdoor from lattices? So the short integer solution problem goes like this. We're given a random matrix modulo Q, and we are asked to find a short vector in its kernel. And in 2012, Micciancio and Piker defined this gadget matrix. That has the same format, basically, as this random matrix from SYS. But here, SYS is very easy for this specific instance. Basically, inverting this matrix, finding short solution, is basically just binary decomposition. And by just playing with a little bit of linear algebra, we can actually build trapdoor functions the following way. Either we're going to have a little bit of G in this matrix in a way that we know, and this is going to make inverting it easy. Either it disappears from this matrix, and it's going to be hard, and both cases are going to be indistinguishable to someone who doesn't know the secret trapdoor key, all right? And so this is just a trapdoor function, but we can also get a whole tree of trapdoor function, an ABO trapdoor function, by basically choosing a lot of them with different traps, doing a little bit of linear algebra. We basically just sum them with coefficient, and we get a trap which is the sum of the trap with the same coefficients. And we can play out with those what we call tags, HI, so that everything cancels out. I mean, this part cancels out exactly for a chosen subtree. So this is what we wanted to do with this all but one branch trapdoor function. All right, so this is going to be our starting point. We need to add two properties, recall. We need to add two properties. We need to add the but one property. So we need to be able to program this trapdoor function once. But that's not going to be very hard. I'm not even going to detail it. Basically, what you just have to do is to make your function affine rather than linear. You just add a small constant, and you will use this small constant to program your function on one specific input. The challenge is to actually generalize binary tree to flat tree. Why? Well, when you look at the previous slide, the trapdoor here was the sum of the TI, okay? With coefficients. And this needs to be small, because with lattices, trapdoors are small matrices. So even if the big TIs are small, we still need this sum to be small. And for that, we need the coefficients to be small. So of course, we can generalize binary coefficient to, like, say, poly n array large coefficient, which give poly n array trees, but that's still not flat enough. We need much flatter tree to make the construction more efficient. So what are our solution here? Again, we need to make this small, this sum kind of small. So what we could do is make it large, but make the modulus even larger so that it doesn't really matter that it is large. But this is extremely inefficient, because not only now the modulus is exponential, which means that each number needs linear the length representation, but moreover, we have to increase the security parameter, et cetera, et cetera. So this is not the way to go. We could try to make the TI to be matrices, and to be small matrices rather than integers. So we can replace the integer coefficient by matrices. But actually it raises commutativity issues, and this sum might not just be a trapdoor anymore. It just doesn't work out. So the solution we propose is to switch to the ring setting. And now we're going to take those coefficients to be small polynomials. And we're going to take all the matrices to be matrices over this ring of polynomials. So now everything commutes, okay, because this TI is now considered a scalar in all those computations. This idea does work, but there is actually a few technicalities. One of the technicalities is the following. It's like for this construction of ABO, we need this property of invertible differences. All right? We need that two coefficients. If they're different, we need their difference to be invertible. And that's not always the case in rings, okay? All the elements are not invertible. So we could do it easily, for example, if our ring contains a subfield large enough. But it does not necessarily happen. Like, even worse for the case that we really like, which is the case of cyclotomic rings for degrees at the power of 2. Well, whatever the modulus you will choose, your ring will never contain a field. So fortunately, we can explicitly and efficiently construct such sets. There won't be subfields, but we can construct them. They will be easily sampleable, they will be short, and there will be exponentially many of them, which is what we need. So that's for the case of powers of 2 cyclotomics. We can also, doing a little bit of algebra, generalize this to other cyclotomic. But really, the construction that's probably the most efficient is this one. All right. So let me conclude. So this was the picture we had before. Basically, what we wanted is to have small signatures, so this one here, but smaller public keys. And this is what we achieved. So we still have the same size of signatures, but the public keys and secret keys are much smaller, which also impacts the efficiency of the scheme. Okay, it's also n times faster with this kind of ABOBO TDFs. I've not described it here, but we also have a variant of our scheme where we get even closer to getting constant public key and secret keys. We get log of log n, but this is at the cost of making the scheme stateful. What's interesting, it also makes the proof, the security proof much tighter. And as I just mentioned, one thing that could be improved in all those techniques is the tightness of the proof. The confined guessing proofs are very not tight, and this is due to all those properties that we ask for, no collision in this tree. So this requires losing a lot in the security reduction. Okay, one frustration about this work is like we had to switch to the ring setting to make it work. Is it actually necessary? Can we make it work for general lattices? Apparently, some people already have ideas about that. And finally, can we get public keys to be really constant amount of elements instead of log n? Since we can do it for RSA-based signature scheme and also elliptic curve-based scheme with pairings, why can't we do it with lattices? Okay, thank you, and if we have time, we can answer a few questions.